Welcome to the lecture series on neural networks and deep learning. This second lecture covers the tricks of the trade in deep learning. And in this first video, I will formulate the aims of this lecture. In fact, we'll ask 3 questions. In deep learning, we use an artificial neural network with many layers. The aim of learning is to adjust the connection weights such that each input is correctly classified, and this must be true not just for images in the training base, but also for future data. In each layer, neurons perform a nonlinear transform, which I call G of A. This is the G in the second layer. This activation itself is given by the sum over the outputs of neurons in the first layer, and neurons in the first layer also have their own gain function, their own transfer function. Now, if you look at standard recommendations for settings of deep neural networks, you probably find that in the output layer, in the context of classification, we should use a sigmoidal unit if it's for a single class, or a softmax function if we have exclusive multi-class problems, in which case we would have several output units, and the softmax ensures that the sum of the activities of the outputs is always normalized to 1. Now, so far for the output, but then we can also look at recommendations for the hidden units, and in the hidden units a standard choice is to use rectified linear units, which are 0 up to a threshold and then increase linearly. And the big question is, why this choice? Are there better choices? Is there a good reason to take this specific choice? Indeed, there are other choices. For example, in the hidden layer, we could also use a sigmoidal unit. Why not? Or a shifted rectified linear unit, or an exponential linear unit, or some sort of piecewise linear unit which is called leaky rectified linear unit. Again, what is the best choice? And so this is the first question for this week. What are good models for hidden neurons, and why? To answer this question, we have to look again at the backpropagation algorithm. You may remember that the backpropagation algorithm works in 3 different phases. In the first phase, there is the forward pass, where the signal is propagated from the input to the output. Then comes the backward pass, where we first calculate the output error, delta, which is then propagated backwards through the network. And finally, we update the weights. But so far, we have not discussed how the weights should be initialized. And this is indeed the question 2 for this week. Why does the initialization or normalization of weights matter in backprop? We'll address this question later today. For our third question, we'll come back to the problem of generalization. We have seen that a single layer network can only solve linearly separable problems, whereas multi-layer networks, deep neural networks, are flexible enough to solve complicated problems with a very flexible separating surface. But as we know, flexibility can lead to overfitting unless we use a smart regularization method, because the network has to work on future data. Now the question is whether there are specific regularization methods that work well in deep neural networks. And this is indeed the third question for this week. What are good models for regularization of deep networks, and why do these work? We start in this question in the next part. So the plan for this lecture is the following. Dropout is a widely used method of regularization in deep networks, And as a preparation for dropout, we need to discuss a standard method that's called bagging. And then we come to the question of what are good units for hidden layers. And in that context, we need to look again at the backpropagation algorithm and see how different units work, in particular the rectified linear unit or the shifted exponential linear unit or similar forms of transfer functions for hidden layers. And then we come to the problem of initialization of the weights in backprop. So overall, we'll talk about vanishing gradient problems, the bias problem, the linearity problem, and about batch normalization to address some of these problems.